Hello everybody. Welcome to our video solutions for Quiz 10. This is from the fall 2021 semester, Math 106, which is integral calculus and differential equations here at Cal State Fullerton. And this last quiz is all about our last topic of the semester, which is Fourier series. And we're going to be doing Fourier series just in terms of computing one, as well as using it to solve or finding a solution to a differential equation. So this first problem, we're just going to find a Fourier series. We're told that we have a function f. It has period 2 pi, so it's a 2 pi periodic function. And we're given the values between negative pi and pi. That's good, because this has length 2 pi. Okay, and the way it's defined is, well, between negative pi and 0, it just is the 0 function. So we could try graphing this. So we're going to go from negative pi to pi. And between negative pi and 0, it's just the 0 function constantly. That's pretty nice. And then once you get to 0, it turns into the function y equals t. So it's going to turn and make a 45-degree angle. So at the highest point here, right, that should be a y value of pi. Right? And then, of course, it's just going to turn around and repeat again, right? So because it's periodic. So it'll go again, pi, and then go up again. Right? And it keeps on going like this forever. Dot, dot, dot. And we'd like to find this Fourier series. So the Fourier series form is going to be a naught over 2 plus the sum starting at 1 of an cosine of, well, typically we would put n pi t over L, where L is the half period. Okay, well, in this case, the period is 2 pi, so the half period is equal to pi. So I'm going to replace L here by pi. But that's nice. Pi divided by pi is 1. I actually can just replace all of this by n times t. All right, and then similarly, I have a sine function, which will also be n times t. Okay, so that's what my Fourier series has to look like, except I haven't told you what the coefficients are. So our coefficients are going to be 1 over, and again, it's the half period, but the half period we know is pi. And then I'll integrate over a base period, so I'll integrate between negative pi and pi. And then I take the function, f of t, times the cosine of nt. And we'll integrate that with respect to t. All right. And of course, we'll do the same thing to get the bn's. So this will be 1 over pi, and we'll integrate from negative pi to pi, f of t, but now it'll be times sine of nt. Okay, so we need to compute these integrals. All right. Now, what's very important, let's scroll back up a second, is that between negative pi and 0, the function has a 0 value, which means when I integrate from negative pi to pi, the first half from negative pi to 0, I'm just going to have a 0 here times cosine of nt. So in fact, I'm going to be able to write this as an integral from 0 to pi, and then from 0 to pi, it's just t, right? So I have t times cosine of nt, dt. And then over here, we'll have 1 over pi. And again, we'll integrate from 0 to pi, t sine of nt, dt. Okay, so for both of these, we're going to have to do a little integration by parts. So let's see what we can do. We'll do, how about some work over here? So if I want to do integration by parts, I'm going to use my tabular method. I'll have t and then cosine of nt. Take derivatives on the left, antiderivatives on the right. So an antiderivative of cosine is sine, but there's an n in here, right, multiplied by the t. So I'm going to have to divide by n to compensate. And then I do it again. An antiderivative sine will be negative cosine. So I'll have a negative, and I'll have a cosine of nt. I have to divide by another n, so I'll have 1 over n squared. All right, draw my lines, plus and a minus. All right, so my antiderivative, I'm just going to put this right in, is going to be, we don't need the integral anymore. Let's see, we're going to have t times 1 over n sine of nt, so t over n sine of nt, minus is plus, 1 over n squared cosine of nt, and this is going to go between 0 and pi. But at this point, we need to pause because we are dividing by n, and n could be 0 for the a's. So that's a problem, right? So this is only going to be, the first line is certainly true. But once we get to this line, this is only going to work when n is at least 1. So we'll have to handle the n equals 0 case separately. That's okay. So what's going to happen? Well, at pi, we're going to get sine of n times pi. Well, when you're working on the unit circle, you know that along the x-axis, the sine value is always 0. So this gives you nothing when t is equal to pi. All right, well, what about over here? Well, now you have cosine of n times pi, and cosine of n times pi, right? There's 1 over n squared here as well. This is just an alternator, right? So this bit here is equal to minus 1 to the n. So that's a really useful thing to know. All right, now what happens when t is equal to 0? Well, now you have sine of 0, which is going to be 0, and cosine of 0 is 1, so we're just going to subtract 1 over n squared. All right, and we can do a little bit of extra work here. We can pull out a 1 over n squared. So I'll have 1 over pi n squared times, I have an alternator minus 1. Now, this is going to break up into two cases. If n is even, we'll get a value, and when n is odd, we get a value. So let's see, when n is even or when n is odd. When n is even, negative 1 to the n will be 1, minus 1 is 0. So we just get a 0 here. When n is odd, we have negative 1 to the n, which is negative 1, minus 1 would be negative 2. So we'll have negative 2 over pi n squared. All right, so except in the n equals 0 case, which we still have to work out, we now know that you actually only get sine coefficients in the odd ends. All right, well, why don't we handle that a0 while we're here? So this is 1 over pi integral from 0 to pi t times the cosine of 0t, which is just 1. So this is just t. Okay, this is a pretty easy integral. So we have 1 over pi times t squared over 2 from 0 to pi, which will be, okay, we'll have pi squared over 2 minus 0. So this is pi squared over 2 pi, which is pi over 2. All right, so that's our A naught. Okay, so now let's head up and do our B's. So for our B's, let's see, well, we're again going to need to do some integration by parts. So let's do that over here. We have t, and we have sine of nt, and we'll take derivatives till we get to 0. Antiderivative of sine is going to be a cosine. We also have to divide by n. Anti-differentiate again, we'll get negative 1 over n squared sine of nt. Draw our lines, plus and a minus. All right, so let's see. We have 1 over pi times, it looks like negative t over n cosine of nt, and then minus minus is plus 1 over n squared sine of nt. And we'll again integrate here from 0 to pi. So let's see what happens. At pi, there's our alternator again. So we get negative, oh, there's another negative though. So this is a negative 1 to the n when you put in the pi, but there's another negative. So we'll end up with negative 1 to the n plus 1. The t becomes a pi, and then we divide by n. And the sine, well, that's going to be just like before, a 0, because sine of n pi, that's always on the x-axis, so that's 0. Okay, then we have to subtract what happens at 0. Well, at 0, the cosine becomes 1. Oh, but wait, there's a t, so that just becomes 0. And sine of 0 is 0, so there's actually nothing to subtract. Okay, but now I have a 1 over pi and a pi. Those will cancel. And I'm left with a reasonably nice expression here. I have an n plus 1 alternator over n. All right, and so now I can put this all together into a Fourier series. So, therefore, the Fourier series for f is, all right, we need to start with a naught over 2. Okay, this is our Fourier series form. We need a naught over 2, and our a naught was pi over 2. So this will be pi over 2, which is pi over 4, plus, okay, let's handle the a portion. So we know that we're only getting stuff in the odd n situation. All right, and note in this notation when I write n odd, we're ignoring any sort of negative n's, right? Because we know for Fourier series that's just not a thing. So we have negative 2 over pi n squared cosine of nt. And then we do the sine portion, and that you get everything, n at least 1. And we saw up above, those coefficients are going to be an n plus 1 alternator over n times sine of nt. And that is our solution. Now, if we take a peek at this over in Desmos, which of course you wouldn't be allowed to do right during the exam, but right, this is just a little proof of concept. This is what the very first term of the Fourier series would look like, in the sense if we made n equal to 1 and we stop there, right? So this would be an approximation. But if we use this Fourier series we just found and we start increasing the n, right? So this would be n equals 3. There's n equals 5. There's n equals 7. And you start to notice it's still wiggling quite a bit, but you see how this wiggle between negative pi and pi is getting a lot smaller. It's starting to get a little closer to 0. And from 0 to pi, well, it's working its way up from 0 up to pi. And if we keep increasing this n, there's 11, there's 15, here's 19, there's 31. You see it's really, really starting to get close to the function we wanted, right? 0 from negative pi to 0, and then looking like y equals t from 0 to pi. All right, and I can take this all the way up here, right? There's n equals 100. And you see, except at these endpoints where it has a lot more wiggle, right, which is suggesting this thing pointwise converges but doesn't uniformly converge. But other than there, it's really, really getting close to the function we claimed it was, which is a pretty neat thing, right? Like Fourier's a genius to see that this could work. All right, we'll see everybody next time.